we could. If you want me to repeat things, particularly for the review classes for the midterms, really just work with me. Let me know what you want to repeat. Let me know if a concept is to some extent not fully understood, then we just go over it again. We have a review class directly before the midterms. So really take advantage for that. Come with specific questions. It's going to be online and remote, but it's something we really should take advantage of. Yes.
Will the midterm also be out on the first quiz?
It's the same format in principle, yes.
Same format, but will it have the same information?
It will have more than the first quiz, so it's cumulative. Everything is cumulative. By the final, you're going to get all the chapters.
Is the final cumulative of the midterm?
Yes. No, it's cumulative, the whole thing. Entire semester. Yeah. Yes? You have a question, Ivrit?
Yeah. I don't remember. I'll remember.
Okay, good. Let me know. Julia? Julia? You had a question?
I was just wondering, the midterm on 14th, right?
14th, yes. Yes. Yes.
Wait, what do you mean that the midterm is going to be remote?
No, the midterm review.
Oh.
We have a week in advance. We have a review session just for the midterms. We're just going to go through everything. It would really be good if you have specific questions that you want to go over, specific concepts you want to go over. Otherwise, I browse through the lectures and I just go bits and pieces and I pick whatever I think is important. We can do either or. All right. Good. All right. Okay, normal curve standardizations and set scores. So this is really where hypothesis testing now really starts. So the normal curve, let's recap. So we talked about the normal curve. It's a specific bell-shaped curve that is symmetric. It's unimodal, and it is defined mathematically. And it's really the foundation of inferential statistics. When it says it's defined mathematically, this is already where I make a quick parenthesis because I want you to have a look at the Excel spreadsheet, normal curve, module 8 normal curve. So it's defined mathematically means this is the equation. And you know these components already. So you know x minus mu, you know mu is a mean, you know sigma is a standard deviation. And here you essentially have 1 divided by this, the sigma, the standard deviation, multiplied by the square root of 2 times p, multiplied by exponential, so that's an ln of minus x minus the mu squared divided by 2 times the variance. And when you employ this, essentially what you get is this. And forget the set scores for now, but here just the values, the deviation of the values from this mean of 7 with a known standard deviation of 2 defines this normal curve. So these are all calculated. And the reason why I'm showing you this is because all of this can be mathematically defined. And all of this essentially is the frequency distribution of a normal distribution curve. So this is what Nolan and Heinz are referring to with saying it's mathematically defined. Yes?
What is y?
Y is, well, it's the frequency distribution. So that's the frequency. So for this very reason, and you will know in a second what that essentially means, but this is just to make the point that it's defined mathematically. And this is obviously important, which we will see in a second, because all of this frequency distribution are essentially representing a fraction of a whole. So when you, okay, sample size is important in relation to the normal curve. So the more sample size you're collecting and you're depicting your sample in the form of a histogram, the greater your sample size, the more likely it will represent a normal distribution. So as the sample size increases, the distribution more closely resembles a normal curve. In other words, as the size of the sample approaches the size of the population, the shape of the distribution tends to be normally distributed. So when you have a sample of 5, yes?
How is that different to the law of large numbers?
The law of large numbers. So the law of large numbers essentially uses with a normal approximation, you're approaching the law of large numbers, you're approaching by repeated sampling the shape of a normal distribution around that percentage. So remember how we talked about, we didn't talk about binomial distribution in that much detail, but if you draw repeated samples from a population, you get a certain proportion estimate from each of your samples that you have drawn. Let's say you have a population of 10%, and you're drawing from this a sample of 100 people. You get a certain proportion of diabetics, for example, from that sample. This is one estimate. So if you draw now another sample, and you estimate again the proportion of diabetics in there, you get another estimate, which is not the same estimate as the first sample. So now you get a number of samples that will essentially evolve and distribute around something, around a mean that will be likely quite comparable to the population proportion, to the population mean. So it basically converges to essentially shape around the true population mean by repeated sampling from your population and getting sample, and that distributes around that true mean of the population. And this is called the normal approximation. So the concept is the same, and there's a very good point, because the concept is the same. By drawing repeated samples, you're basically shaping the distribution of your sample estimates. And this is true for the binomial distribution, and that is also true for the exercises that we will be doing once we get to samples. But this comes later on. So this is a very good point. Essentially, law of large numbers, you draw something repeatedly, and you get a certain probability estimate that gravitates around the mean. And this different samples that you draw will essentially shape a normal distribution. That's a normal approximation, how it's called. Good point. So when you have a sample of 5, and this is now the country's happiness score, this is the Excel spreadsheet that I have posted on the canvas. So I have digitalized that, I've put it on canvas so we can play around with it a little bit. So now we have a sample of 5. You can assume there's something resembling a normal distribution, but it's not really a normal distribution. If we're increasing now the sample size and we take a sample of 30, we're getting something that is a bit more looking like a normal distribution. If we go up now and we take the entire sample, or majority of the sample of 157, then it starts to really look like a normal distribution. And this is to make the case that the more sample size you are looking at and depicting, the more likely it will have the shape of a normal distribution, naturally. So as the sample size increases, the shape of the distribution becomes more like a normal curve. Can you think of a variable that might be normally distributed? Think about it. Can nominal categorical variables be normally distributed? And this essentially gets to that point. If you have a nominal categorical variable, and this goes in the question that you asked, they're not normally distributed, but their distribution per se in a population might be. But they themselves are not normally distributed. So the occurrence of a nominal variable might be, in terms of the frequency, normally distributed. So this is what you use for a binomial distribution, that you estimate the variability of a sample estimate of a characteristic in a population by essentially doing a normal approximation. So you use this repeated sampling, and you basically you see the shape of a normal distribution around, but it's per se, it's not normally distributed. But the approximation to the true population mean or estimate or proportion would essentially be. So now, what variables would you think are usually normally distributed? Like usually you find many variables normally distributed, particularly those in the realm of physiology, those in the realm of medicine. A majority of them will be normally distributed. There are some that are classically, traditionally skewed, some others are not, but a large number of variables are normally distributed. Classical variables are, for example, age in a population. Age in a population will likely be resembling a normal distribution. Body mass index, weights, all these things will to some extent resemble a normal distribution. And when thinking about a normal distribution, we're basically getting to the next part of it. Given that the normal distribution is symmetric, bell-shaped, and unimodal, you can employ something that is called standardization, where you have on your histogram, on your normal distribution frequency distribution, you can essentially standardize the entire normal curve in relation to their center, which we know the central tendency to be the mean, or the mode, or the median, but essentially it's around the mean. So in a symmetric normal distribution, the mean is going to be the center. And this center, as well as the variability of this normal curve, can be characterized using the so-called STAT-score. And this STAT-score allows for the calculation of each individual point on this normal distribution, on the entire magnitude of values that you have available for your data. That means that essentially each of these data points will essentially be a certain point. So let's say you have age of a population. You have the mean age here in the middle at the center, building a STAT-score of 0. Then you have a STAT-score of 1 from that age will essentially be one standard deviation above the mean. Whereas a STAT-score of -1 is essentially one standard deviation below the mean. So essentially you're using at this point the mean and the standard deviation to characterize your normal distribution. Any question to this as a concept? Yes.
How does the z-score relate to standardization? Like what does standardization have to do with the z-score?
Standardization is done using the STAT-score. So you essentially standardize the normal distribution curve from the actual magnitude that you're depicting as a histogram. You're depicting it and standardizing it to STAT-scores by using the center, the mean, and the standard deviation as a Markov variability of that normal distribution curve, characterizing the shape and form of this normal distribution.
But if the first histogram is not normal, then how do you get to the z-score?
Well, if it's not normal, then you have a problem. then it's becoming more complicated because the STAT-score is essentially so you have parametric and non-parametric testing. We're doing in this class only the simplest forms of analysis, which is parametric testing. And parametric testing has a basic underlying assumption, a normal distributed data set, normally distributed data. Non-parametric testing, which we will only do one test the entire semester, which is the chi-squared test, where we're comparing counts against each other. This does not have these underlying assumptions, and you do not need normal distribution as the underlying necessity condition. Okay, any questions on the normal distribution? So we have the center is a set equals 0. A set equals 1 is one standard deviation located away from the mean, above the mean. And the set of -1 is one standard deviation below the mean. Simple so far, right? So now the calculation of a STAT-score, of any particular STAT-score, is now done in the same context as STAT equals the individual x. So your score that is of interest for you, for which you want to calculate your STAT-score, x minus the mu, that's the population mean, divided by the standard deviation. So when you go back to calculating now the STAT-scores, so you have here the happiness score. You have a mean of 70. This is the happiness score of the countries. You have a standard deviation of 10. That means that going one standard deviation up. No, it's not done.
Wait, what is X?
It's not done.
What is X?
X is every individual point.
You have to add them
So add them together. No. And so this is essentially, so let's think about the happiness score. Let's assume the happiness score distributes around a mean of 0. And these are all the happiness scores of the different countries. So this data here indicates that the set here is 0 at a mean of 70.
So 70, what would be X? 70, you can choose any number.
You can take any number. So if I do here an X of 80 and I say, okay, so my X is now 80. I get an X of 80 minus the mean of 70 is 10. And assuming a standard deviation of 10 gets you 10 divided by 10 equals a standard deviation, equals a set equals 1. So this is essentially how this formula materializes. So it's any X of interest minus the mu divided by the standard deviation. Gets you to any X that you're interested in. Also, when you are interested in lower numbers, so let's take 60. So we do 60 minus 70 is minus 10 divided by a standard deviation of 10 is minus 1. Simple, right? Yeah, that's the trick. That is the trick, because so right now we're doing set statistics, and this will be what we're going to do next class on Monday. So we will do hypothesis testing with a known population mean and the known population standard deviation. And I'm flagging this already because this is essentially what you will know for the second half of the semester. It will be very central that you will recognize in a question. And this is where it's important to kind of cumulatively keep pace with the class, because you essentially, you get cues from the research question at hand, whether you are employing a set statistic or a t-statistic later on, where you're estimating the standard deviation from your sample. Right now, the standard deviation will always be given. So right now, you need to know, to employ a set statistic, you need to know the population mean, or that number you're comparing your sample mean to, and the population standard deviation. So a good question, very good question in this context. So now the obvious question is, not yet, but essentially, you can, using this standardization, you can use based on a normal distribution of whatever parameter you're interested in. For example, the size of a dog, you can compare positives from negative set scores. So you can say, I have now a dog that is greater than the average dog, or I have a dog that is smaller than the average dog. So positive and negative set scores. So the one on the right is the positive dog, right? The one on the left is the negative dog, the negative set score dog. So do we want to practice this? That could be a good approach at this point. So for this very reason, I've included this. It's considerably easy, but essentially goes in the same direction as this spreadsheet here. Because when you see here the characterization of this normal distribution curve at around the mean of 7 with a standard deviation of 2, you see that here you basically have from 7 to 9, the band was from 0 to 1 set score. And in the same fashion, you have from 7 to 5, the range from 0 to your -1 set score. So now bringing this into practice using the country happiness scores. So you essentially, you would first, when you get presented with data like that, and you're being asked to characterize this normal distribution, you would first calculate the mean. This is, yes. This is the Excel spreadsheet that is posted on Canvas, the happiness score.
This one?
It is it? Happiness report, raw data. Can you access it? Or did something fail with the posting? Is it accessible on Canvas?
Yeah.
To happen? Okay. Okay, so first step. So the first step is always the calculation of the mean. So you will need to know what your mean is. So you are calculating average of B2. Yeah. Bella? Okay. Okay, so the mean is now B2 to the very end of this list of happiness scores, which is here 158. So B2 to 158, essentially, like this. So average to B2 to B158 gives you a mean of 5.382. Correct? Average, yep. Average B2 to B158.
Where should be in I3?
In, excuse me?
That's it, where should we have this? Where should we
It's like, it's probably easier if you do it in the same column as I did. So I have it on I3, the formula.
Wait, what we put in
It's equal average B2 to B158. Get you the mean.
what does it look like up there? Wait, is this the colon?
This is colon, yeah.
B2, then
Colon B158. Yeah. So what you want next is the standard deviation. So your standard deviation you calculate just like you can confirm yourself is by stdef.p B2 to B158.
So you don't need to do like the lower calculation?
Okay, yes, you're right. You're right. You're right. Okay, good. Okay, we're doing deviation. So deviation. Okay, no, it's fine. It's actually good. It's actually good suggestion. Okay, so just that everybody sees this shoe again, how to do that. Okay, so deviation is C. So we do B2 minus the mean. Important was doing this subtraction from the mean is that you lock the cell in. You do $I, $3. You get one deviation. B2 is that individual X. So all these entries, that's your X. Yes. Yes.
Does it matter that I did a round line? So if my numbers should be a little bit different.
That you round?
I did it round my seeds.
That's fine. That's fine. The number of decimals is not necessary. It's like as much as you want. So, okay, so this is the deviation. The deviation is the individual X minus the mean. So we're getting $I, $3 gets you to the locked mean. Yes, Julia.
I just got a different answer than you did. I
That-
got 7.536
For what?
for deviation.
So are you calculating B2 minus $I, $3?
Yeah, 8. It's possible that you're just not
You need to direct the second calculation. It needs to subtract it from the. It needs to subtract the mean from the X. Yeah. Okay. So now you can complete this all the way down. You just double click the right lower corner.
Can you repeat the equation?
B minus $I, $3. And once you have this deviation, you just need to square the deviation. And the squared deviation is essentially C2 little hat 2. Gets us to the squared deviation. We click on the right button, right corner. Now we're essentially building the sum of square. Okay. We're doing, okay, let's focus, let's focus. Okay, we're doing x, b2, minus the mean, $I, $3. Now you square the deviation.
Wait, this is in box D2?
This is D2, yes. So D2 is C2 squared.
Oh, I got a number. And then
C2 squared, yes.
I got like the hashtag. I mean, wait, do you have to log it in?
Can you expand it?
Like all the way down.
Are we able to square? Who has problems to square?
Where are you at? This one?
Yeah.
This one? Yeah.
Okay, 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 concentration. If you have here little hashtags, you just need to expand. You just need to expand it. Okay? So if you have something that looks like this, you basically click here on the side of the cell on the column, where the column starts, where the cursor shifts a bit, and you basically can change the size. You see that? And then you can expand it, so it shows the numbers again.
So for deviation, you just did
So the deviation is just a deviation of the individual score from the mean. The squared deviation is the squared deviation, nothing else. And for the sum of squares, you only need to build the sum of D2 to D158. That's the sum of squares.
I mean, can you show us
Which one?
the 203?
Sum of D2
Like not what?
to D158. That's the sum of squares. Yeah? Good, very good. So once we have the sum of squares, we need the variance, right? And the variance is calculated as the sum of squares. Sum of squares. Sum of squares. It's
D2 to D158. Oh,
sum, yeah. Dividing the sum of squares by the number of entries, which is count, E2 divided by count, D2 to D158, gives you the variance. The standard deviation is calculated as the variance square rooted. So square root of the variance is the standard deviation. Yes.
wait, can you, a couple of us are missing the
This one?
yeah, I didn't get the deviation and the square deviation.
Exactly. Okay. Okay. Excuse me. Yes. Yes, we go through it once again. Silencio. Okay. B2 minus the mean gets you to the deviation, right? Taking the deviation squared gets you to the squared deviation. Summing all squared deviation
How do we plug in those numbers?
which ones? The squared deviation?
Yeah, like all of it. Just drag it.
Just drag it all the way down or do this. You do equal sign, deviation squared, enter. And now you click on this little button. You see, you just put it all the way down. Hmm?
Square root. Oh, yeah. square of the sum of, or the square root of the radius.
The standard deviation is the square root of the variance. The variance is the, so next. No. No, you can leave look, standard deviations, our decimals. If you leave more, that's perfect. That's fine. That's fine. It's like usually there are not many reasons why you would do more than 2 decimals. Very seldom that you need more than 2 decimals. But yeah, in general terms, yes.
Okay, I know standard deviation is the square root variance, right? But how do you find it if you don't have to?
Which one?
Both.
Okay, so you need the deviations. Then you need the squared deviations. Then you sum all the squared deviations. Then you get to the variance. The variance is the sum of squares divided through the number of entries. And the number of entries is quantified as count D2 to D158.
Oh, yeah. How do we get the same squares? Is these two?
So when you want to propagate a formula and you just want it to complete all the way down, which your list goes, you go on. So if you want to square this, you want the squared deviation. You enter the formula. You do here C2 squared. You get it once. And then you go here to the right lower corner. Everybody pay attention for a second, please. You go to you have a formula. You want to complete this all the way down your list. You go to the right lower corner where it changes to become this little cross and you just double click it. It will continue the formula all the way down to the end of your list. Yeah? And then you basically go to sum that up. Sum D2 to D158 gets you the sum. Taking the sum of squares, dividing it by the number of entries, which is calculated as count D2 to 158, gets you to the variance. And the square root of the variance gets you to the standard deviation.
Okay.
That's your standard deviation.
Wait, what's the point of number of entries?
Well, number of entries is just because I have the formula right in here, right? I have count D2 to 158. And this is just showing that formula explicitly. Okay, so that's the standard deviation.
Can you put that standard deviation one more time? Square root of the variance.
Square root of the variance. Yeah? All right, and now we just need to move the standard deviation here over there by equal sign, and we just select the standard deviation, now it transfers it over.
Oh, you just tried it?
You just say, no, you just say equal sign, and you say equal sign is this number. Yep.
Can you please do the variance one more time?
Yes.
Thank you.
Sure. E2 divided by the count of D2 to D158. Yeah?
Yeah, thank you.
And now the square root of that gives you the standard deviation. Okay, so why have we done this? Because now we want to go. So who can tell me the SAT score of Germany? SAT score of Germany.
Where is
Where's Germany?
17.
17, yeah. So the formula for the set score is x minus the mu divided by the standard deviation.
What would be the X in this case?
Germany. you have an entry for Germany, which is 6.994. That's your x. So what you have used now to characterize, so you basically built a normal distribution now virtually, right? You build a mean, you build a standard deviation. So you have now a mean, which is your mode, your unimodal center. And around that, you have a normal distribution now of all your countries, 157 countries. Yep.
So can you just do the deviation divided by standard deviation? Isn't the deviation at times that?
It is x minus mu divided by the standard deviation.
That's deviation.
That's the set score.
Nothing, x minus m is deviation.
X minus m is the deviation, yes?
So can't you just do deviation divided by standard deviation?
You could, yeah. Comes to the same end, yes.
What's the difference?
Well, usually you wouldn't calculate it like that, right? Usually you would just do an S and the STDEF function. I'm just going step by step, right? Yes, you're right, of course, yes. Not at all. It was an example, it was a random example. I looked at it, I saw Germany, it's like, okay. You can also give me the happiness score of Belgium. How about Belgium? They have 6.994, yeah?
Yeah, so that's.
That is a set score.
Okay.
And what is the set score? So, no, but this is, yeah. So now we have this formula, right?
6.994 minus the mean divided by.
Here we go. Yep. So now we have the example of Germany has now what set score? So we have B17. Oh, well, don't forget the bracket, please. Don't forget the bracket. Forget mathematical operators. Minus. You need brackets. You do. Absolutely, you need them. The parentheses. Yeah. Parentheses round, bracket squared. Good. I kept on mixing them up. So. Yeah. Parentheses. Yeah. This is a parentheses. Round is parentheses. These are the brackets, and then you have the curly brackets. Yep. Okay, B17 minus the mean, parentheses closed, divided by our standard deviation. Good. Okay. Divided by the standard deviation. You just take it from here. Equal sign, this one. Yep. I like to duplicate things. I just wanted to bring it in the same column, right? So there's no real point to that. Okay, so that was our first calculated set score. So, next one. What? Israel. Good. Let's do Israel. Good. Let's do Israel. We do parentheses 7.267 minus the mean, parentheses divided by the standard deviation. 1.65. Okay. You can just check it. Yeah. Okay. That's now to make it a point. So, Yes,
Couldn't this be something that you use a dollar sign for? And just drag it out?
you could, yeah.
Okay.
You could, you absolutely could. But what will it show? What are you expecting then? You get all the set scores, right? Yeah. So what will happen? Of course it works. Of course it works. Set score. Okay. So this is now this. Oh, parenthesis. This minus the mean divided by the standard deviation. No? Oh yeah, dollar sign. Good point. Good point. Thanks for the reminder. Dollar, dollar. Yep. So these are the set scores now. The dollar signs are locking in whatever you want to lock in. You want to lock in the mean. You want to lock in the standard deviation. These are the two constants in your calculations. What you want to change is your x. And now you can.
These where you take the thing.
You take the thing, the yes.
And then you subtract it from what?
You subtract the mean from your x.
Oh.
Your x is the entry for each individual country.
Wait, how do I get my C-scores in such an E? I can't move it.
What can't you move?
It's your arrow. Okay, so which one do you click on? This red.
So if you go now on the right lower corner, you're completing this for the set scores.
Whenever I try to do the order, it doesn't go like that. Oh, I got it.
No? Well,
Do I have to select the whole column?
Make sure it's.
no, you don't have to. It's if it's one formula, it goes all the way down. Yes, Esther.
So we take the entry as a double joint. Sorry. And then what do we do with this?
We're taking the individual entry minus the mean in parentheses divided by the sigma, by the standard deviation.
Divided by 10.
Yeah.
Divided by standard deviation.
Correct.
We only lost the mean, like.
You only lock the mean and the standard deviation. You lock what is locked, right? These two don't move. Your x, you want always the x in the respective row. That you want to shift down. When you look here at the formula, this takes this x, but still this mean and this standard deviation. Yeah?
We always lost the mean.
Not always, but in that particular example, when you need it that way, you do that. Huh? Yeah?
What's the significance of locking down standard deviation?
Because if you pull this down and you complete this all the way down, it will shift with each row your x, but the mean shouldn't shift. So you always want the same cells. You tell Excel to only take these two cells, and you're locking the cells in.
Wait,
That's
how am I getting all these weird things? And I need to figure that out.
We can look at it later. Okay, good. So this is the calculation of set scores, right? So this you're essentially doing to characterize your normal distribution curve. So you basically get now an X specific set score. If you're going now further, you can logically also rearrange this formula, and you can calculate the X by calculating it the other way around. So if you have a given set score, you can calculate your X. You can calculate the happiness. So what's the country that is closest to a set score of 1.3? 1.3.
Brazil.
Brazil?
Oh, no. Luxembourg.
Luxembourg. All right. How about 0.7?
0.7.
Yeah.
Trinidad.
Good.
Wait, you're looking at the happiness score?
Yeah. No. You're looking at the set score. because each happiness score corresponds with a set score.
What is
Whereas the characterization of yes, C-score. Yeah. Yes. Yep. All right. The happiness score is not the set score. The set score is essentially characterization of the normal distribution curve. Good. All right. So, yes, Julia. The dollar signs comes in front of the column and in front of the row. Okay, good. So we've been here. So we essentially can now, on the other way around, we can actually now rearrange this formula to calculate a specific x by knowing a set score. So if so rearranging, right? So you need set multiplied by the sigma plus the mu gets you to an x. So if you if you essentially a set score of 1.3 equals 1.3 multiplied by our standard deviation plus the mean. So the happiness score corresponding with that would be 6.86, which we know already is Brazil, right? Or Luxembourg. Luxembourg, okay. So we have 6.86. 6.86 is somewhere here between Luxembourg and Ireland. Yes, Julia. Yeah, so thank you, Karen. Okay, good. So this is essentially how you can approach it. So you can transform one into another. You can make an x a set, and you can make a set an x. Good? Good. So why is this important? Because we're characterizing a normal distribution curve now. And by doing so, you're essentially allow yourself to compare apples with oranges. Because let's say you have an apple has a different size than an orange, but you still want to know whether the apple that you picked is kind of as much greater than your orange as compared to the mean of all oranges and compared to the mean of all apples, right? So you make one thing that is usually traditionally not comparable to another variable that essentially is also not comparable to the other, but comparable and relative to the mean. So you standardize to your mean and your standard deviation by using the standard deviation. So essentially you convert your normal distribution of all your normal distribution entries of all your values to set scores, a normal distribution of set scores, in order to make it comparable. So why do you want to make things comparable? Because sometimes you want to compare things that are traditionally not comparable. So this is, so in research, for example, you can do it by essentially trying to find out to what extent are emotions comparable to each other. Traditionally, you would quantify them in a different way, right? So you have all emotions, you have fear and disgust, traditionally not comparable. Would be a different scale, different marker, something totally different. But you compare them to each other by essentially creating a mean, a quote unquote prevalence of the population. It's like how many in the population feel fear, how many in the population feel disgust, and how many feel any emotion. So essentially you're creating a framework in which you can compare markers that you usually cannot compare. This is why you take the mean as your reference point, and you're depicting all data that you have at your disposition in relation to that mean by using the standard deviation as a population marker of variability as your tool to standardize them. Does that make sense? Everybody with me? Okay. So now when you think of a population, that's not what ends. Because if you assume your normal distribution, a symmetric distribution, and the distribution that essentially has minima and maxima, so a minimal value and a maximal value, you get within this entire range something which is called the area under the curve. So who remembers integral? Integral. Integrals, yeah, integrals under a curve where you have a function, you have a mathematical function, and you calculate the area under that function. You're doing the same thing, and you remember that function that I showed you in that Excel spreadsheet. You have a function now that basically describes this bell shape. And you can quantify that entire area under that bell-shaped curve as 100%. So you're saying all of this is 100%. If I go from the mean, 1 standard deviation above, I get 34% of that entire number of entries. I get 34% of my population. If I go 1 standard deviation below the mean, I get 34% less than the mean. I go 1 standard deviation above and 1 standard deviation below the mean, I get 2 standard deviations, I have 68% of my population covered. If I go 2 standard deviation up the mean, 2 standard deviation down from the mean, I get 95% of my population. That's the empirical rule. So it's an approximation to what percentage of your population is contained within that mean. If you go 3 standard deviations up and 3 standard deviations down from the mean, below the mean, and you go 6 standard deviations, you capture within 6 standard deviations, you capture 99% of your population. That's the empirical rule. And I'm flagging this as a quiz question. This is a very low-hanging fruit. But make sure you know when to use it. The empirical rule. To estimate the number of people that have a certain value. So if you, for example, if you say, okay, so I have now blood pressure, always my blood pressure, right? So you have blood pressure, you have a center of 120. And you're saying I have in my population a standard deviation of 10%, of 10 millimeter Hg, which is the marker that you express it. You say, okay, so up here at 1, I have 130, and minus 1 would then be 110. So I can say I have 68% of my population in the US is between 110 and 130. So it's an extremely powerful tool to describe your population, right? Once you have that standard deviation given and that mean given.
Wait, can you explain that again?
So you have the normal distribution distributes around the mean, right? You characterize your normal distribution according to the standard deviations. If you assume a blood pressure of 120 as being the mean blood pressure in the population, whatever that population is, and you have a standard deviation of 10, you can define, so a z-score of 1 is 130, z-score of -1 is 110. So then you can say and conclude that I have 68% of my population between 110 and 130 millimeter Hg blood pressure.
Why 68%?
Because you assume the entire function to be characterized by 100% up to like the maximum, because it gets thinner, thinner, thinner. It will never touch. By the way, this normal distribution, this function never touches the x-axis. It will go all the way to the maximum. So, okay, so 68% here, 95% here, 99 on 3 multiplied by 2 standard deviations. Yes?
Is it ever 100% or no? Because you said it doesn't touch the x-axis.
Well, you will never get to 100%. That becomes a little bit of a harder conversation piece, because this becomes, for hypothesis testing, this essentially becomes the quote-unquote p-value, which we talked about last class with the 5%, which everybody's after, because the z-score of 1.96 corresponds with a 5% p-value. upon which you're rejecting your null hypothesis. So this p-value never gets 0, it just approaches 0. And the smaller it gets, the more likely you reject the null hypothesis, but that's later. For rejection, you need to get lower than 5%, but it can be so low that you have like R doesn't even display the decimals anymore. So, but yeah, it never gets 0. Good. Any questions so far? Yes.
Is the graph going to have the percentages underneath, like so you can?
Excuse me?
Is the graph going to have the percentages underneath, like right there? Like
Yes. Yes. So this is 0 and -1,
Yeah.
34.
So every graph that we see
Exactly.
determinants will have the percentages.
Exactly, because it is symmetric. By that, you can basically 1 to -1 is always 68. Empirically. Okay. And now we're gonna go back to the PDF. So how many? Oh, 50 more minutes. Good.
Wait, what's two standard deviations? What percent?
95. So now we have the set score table, because we're not satisfied with an approximation, right? We want to know. Now we want to know in detail. I like we're on the same page. That's good. Okay. Okay. So we have now a set score that essentially we can, and there's even a tool that is even more accurate than that, because this is already only going down 2 standard deviations. So we have here the set score table. The set score table that I have provided you with is slightly different than the one that Nolan and Heinzen will talk for you. I provide to you. I find this one to be the more intuitive one. So this set score table ends on page 1 with 0, -0, which good, and starts on the second page with 0. At 0, it's exactly 50%, right? So now when this set score of 0 is 50%, the set score of 0.01 is 0.504. So with every set score, with every increase of a decimal, you see an increase in the percentage. If we're going to a set score of 1, what do we see? 50 plus 34. Because we know that above the mean, we have 34%. So the set score table essentially gives you a proportion of that area under the curve that is below or above the mean. So if you go 1 set score up, and this is set score of 1000, it is 0.8413 or 84.13%. If we're going to a set score of 2, we get to 97.72.
What was that thing you said, 50 plus 34?
50 plus 34 is this. 34. 50% goes all the way to the center where we have a symmetric.
And then 34 was
Yes.
1.
Yes.
Which basically tells you the percentage.
Correct. So here we have a set score of 2, which is 2 standard deviation. And this is why the empirical rule is only an empirical rule, because here we say 0.9772, right? So this is not the 95% I was talking about. So this is where it becomes an empirical rule, because it is only an estimate, nothing else. So you're basically getting to 0.992, and with 3 you get to 0.999, which is essentially 0.9987, right? So this is also substantially different from the 99%. But essentially, this set score table allows you to quite accurately find out your percentiles.
So it's the same for every table? It's the same for every chart?
The principle is the same, yeah. The principle is the same. So this set score tables allows you to essentially quantify the fraction of a population which is below that set score of interest or that X of interest. So this is how you create percentiles. You estimate percentiles. Make sense? So this is all which we're discussing about set scores today. Any questions so far? So central limit theorem. This is the last thing we're going to do. So that's 10 minutes. Okay. So the sample means are normally distributed even when the population from which those were drawn is not normal. A distribution of means is less variable than a distribution of individual scores. So now we talked about individual scores. So these are all those countries, right? If you are now, now let's take a step back. Now we have 157 countries. So now let's assume this is the quote unquote normal distribution of these 157 countries. If we are now drawing, and this is now conceptually, you're gonna walk with me along. Let's assume you draw a sample of 10 countries. You get 10 different happiness scores out of those 157. These 157 happiness scores will build a mean. So now you remember that mean, and you drop those 10 countries back in your pool of countries, and you draw another 10. You draw another sample. You get another mean. And you do that 100 times, or 10, let's say 20 times. You draw 20 different samples. These 20 different samples will give you 20 different means. These 20 different means will, once you calculate the mean of those means, resemble the mean of your population. Because the mean is the mean of your sample is meant to reflect the mean of your population, right? So a sample is a subset of a population which serves for you to quantify the central tendency on the dynamics within a population. So you mean to have a generalizable sample to get a mean, and that one mean is meant to reflect the mean of your population. And if you get repeated samples, you get a certain number of means from each of these samples. And the distribution of these sample means will essentially more likely resemble a normal distribution. And the mean of these means will very likely represent the mean of your population. And this is the so-called central limit theorem. And the central limit theorem is that the mean of the distribution tends to be the mean of the population. So if you have different means, and you have your 20 means now, and you map this distribution of those 20 means out as a sample distribution, and you calculate the mean of this sample distribution, this mean of the sample distribution reflects the mean of the population. The standard deviation of this distribution of the sample means is going to be smaller than the population standard deviation. Why? Because your mean is a better estimate of the population mean than what you have from those individual scores. Individual scores vary widely. You have like the very happy countries, you have the very unhappy countries. It's a much wider distribution than these randomly sampled smaller samples that have allowed for you to estimate one mean, two means, three means, up to 20 means. Well, can be how many samples, however you want to study. So the entirety of these sample means built this distribution of the sample means. The mean reflects the mean of the population. The variation of these sample means is smaller than the variation and variability and the standard deviation of the entire population. By that, you essentially get it from that shape, which is wide, to a more narrow shape, where all these sample means essentially only build a smaller standard deviation. Why is that important? It will become very important for hypothesis testing. Because this standard deviation at this point is not called a standard deviation anymore. It becomes the so-called standard error of the mean. And the standard error of the mean relates to the standard deviation of the population by standard error of the standard deviation divided by a square root of the sample size.
Are we calling special size n?
Because it's the sample size, well, that is a good question. N is just a reflection of the count. That's a naming convention. So N is the count of your sample. So if you have a sample of, let's say, 10 countries, your N is 10. The standard deviation we quantified as 1.13. So you would calculate 1.13 divided by square root of the sample size at 10. So that would give you the standard error of the mean. So you essentially, you have repeated sample means. You have one sample, you assume that this is the mean of a repeated sample. You assume this to represent the population mean. You quantify the standard deviation around this sample mean, this estimated population mean, by taking the standard deviation divided by the square root of the n, getting you to the standard error of the mean. And this is where hypothesis testing will start. Good. Why is this important? Because you have with this happiness course, you have a wide distribution. The distribution of the means makes it narrow. The advantage also is that this also makes it more likely that you're looking at the normal distribution, because even if you have severely skewed scores and severely skewed distribution of the population, your distribution of the sample means is still normally distributed. So you are still safe under the assumption that all your underlying distributions are normal distributions. And with this sample distribution of the means, you can just in the same fashion as we have done before, and this will be what we will be doing with hypothesis testing, we can quantify a set score. This time around, using the mean of your sample minus the mean of the population of which you have drawn your sample, divided by the standard error of the mean. And this will allow you to compare the distribution of your sample from the distribution of your population. And this is essentially the mainstay of hypothesis testing. Good. I conclude for today at 6:15. I think you have a class to get to. Right? All right. Thank you.
I didn't hear you call my name first.
Yes, you may not have been here. Remind me. Esther Rosten. Yes, I remember.
Also, I haven't missed the class. I haven't missed the class, but I have an 83.
You have an attendance missed? No?
I never missed.
Oh,
I don't
okay.
have 100.
Okay, you have never missed? Okay. May you have come late?
Oh, one day I remember.
That may be.
Well,
Send me a reminder. Send me a reminder. Okay. Hi.
Okay, so I have these weird thingies, and I just want to know.
Okay. You probably did not lock.
Emma, it's not.
Yeah, you didn't lock this guy. You need to lock the column and the row. Yeah.
Thank you so much.
You're welcome. Yes.
My percentage is coming up like this.
That is wrong.
What?
It's wrong.
Yeah, I know. I don't
Okay,
know
good.
why, but look, I'm doing it the right way.
You are calculating. So this is your proportion. This multiplied by 2. That is weird. Oh, did you convert it? Oh. Careful with formatting cells. So it assumed. See?
So those are wrong, because there's not, they're not supposed to have bigger.
Yeah, you gotta make sure that you didn't change the formatting of the cell.
I don't think I did. So
Uh,
all these shouldn't be such big numbers.
oh, these look fine. They look fine.
Okay.
That's 10 to 14. Yeah, that looks good. No squares. Yeah. That's good.
Okay, and then for here, I'm supposed to be doing it based on like by group, right?
Yes.
So that's fine. That makes sense.
Looks. Yep. I don't know. I don't know the number. But sure. Yes. Hi.
For the bar, for the bar chart, what were the values that we were looking at? Was it
This is the first bar chart. This is the price, the average price.
the income or the price?
Average income, the average that you calculated. Yeah. You did all the calculations, and then it's the average income. Yeah. Yeah.
Okay, and then when you want to like describe what we see in the charts, is that enough?
Yep.
Is that enough to describe like what we see in the charts? Like what else do we write?
Yes, as price increase. Yeah, that sounds good. And the income, also describe the income.
From this chart?
From
Like that was.
yeah. No, then it's fine. Yes, the shirt is fine.
I'm like doing it right. How do I know? Like
Yeah, that's the trick about it. Yeah.
Like me and my friend, like we did like I checked the
Yeah.
answers, like they're very different. Like I don't know if you're right or wrong.
Well, does it look right? Did you do all the calculations as we did them?
Sense, like
Did you use a function?
see it? Is this enough to describe?
That's a function, right? Now. Did you calculate the deviations in the
I
square?
did all of this stuff.
Yeah, no, these are functions.
Yeah. And then I calculated that with
No, but you want to calculate the deviations of the square deviations, right?
yeah. How do you calculate deviation?
Like we did today.
Which function is that?
Hmm?
Which function is it?
That's no function. We don't use functions. That was what I talked about in the beginning. No functions.
How do I answer labels?
Just click on the axis, and there should be somewhere in charts, chart format, chart design. Axis titles. There we go.
Okay. And what the X is
The price.
and the
Is
Y
the
is the
quantity of shirts, I believe, right?
Oh, I'm not doing 3 separate ones.
No. Just overall. Yes. For each price.
So how do you do the bar chart? I don't know how to do that.
Well, it's the average income, right? You just go and insert chart, and then you can select which date range. No, that's just a bar chart. Yes. It's one of these.
How do I want it? The first one?
Yeah, that looks nice.
Which, I don't get what it means, a bar chart of average income. So I go,
So you have 3 average incomes for each group. You just create a bar chart of that. That's it.
what format should you
Yeah.
handle it?
That's it. Just label it.
It should be in Excel format when we handed it. It should be in Excel format when we handed it, like.
Yes. With all the calculations. Thank you. Looks okay. Yeah. Yeah. Do you have all the calculations?
I didn't finish it yet. I did income deviation. I didn't do square deviation yet.